You ask a chatbot to fix your code, then to write a poem, then to explain a tax form. Same AI, 3 completely different jobs, and it answers each one fast. Here's the strange part, a model that knows that much should be slow and expensive to run, and somehow it isn't. In the next few minutes, you'll see the trick that makes it possible. The secret is that the giant AI you're talking to isn't really one giant brain. It's a crowd of smaller specialists, and for your question, almost all of them stay asleep. Let's open it up and watch who actually wakes up. This is Glass Box, where we make the hardest ideas in AI feel obvious. Today's question, how can an AI be enormous in what it knows, yet cheap and quick to run? Last time we saw the memory trick that keeps a chatbot fast as the conversation grows. But there's a second, bigger cost hiding underneath, the sheer size of the model itself. Make a model bigger and it gets smarter, but if every part has to switch on for every word, the bill explodes. We want all that knowledge without paying to run all of it every time. That tension is the whole story today. Here's the plan in 5 steps. 1. Why one giant brain is the wrong picture. 2. The team of experts. 3. The router that picks who answers. 4. Why most of the model stays asleep. And 5. We follow a single word through the whole thing live. Part 1. The wrong picture, one giant brain. Picture the usual idea of a big AI, one massive network where every word you send flows through every part of it. Nothing is skipped. To answer hi, it lights up the exact same gigantic machine it would use to debug a database. So with this picture, there's a cruel trade-off. More knowledge means more cost to run, locked together. To get a smarter model, you seem to have no choice but to make a slower, pricier one. That's the wall we need to get around. That all-on design has a name. A dense model, dense meaning every part is active for every word, no gaps. Turn the model bigger and you don't just store more, you compute more every single time. Real example, like a building where the lights, heat, and every machine in every room switch on the moment one person walks in the front door. Powerful, sure, but you're paying for the whole place to answer one visitor. Part 2. The team of specialists. Here's the first move. Instead of one enormous all-purpose network, you build many smaller ones, side by side. Each one quietly becomes good at a different flavor of language, and we call each of these little networks an expert. One quick, honest note, these experts don't come with neat labels like the grammar one or the math one. Nobody assigns them. They drift into their specialties on their own, just from being trained, so the boundaries are fuzzy and overlapping, not tidy departments. The hospital picture is the feel of it, not a literal map. But a room full of specialists raises an obvious problem. When your question walks in the door, who decides which specialist should handle it? So what's an expert? It's just one of many small subnetworks inside the model, each tuned toward a certain kind of pattern. Maybe one leans toward code, another toward everyday chit-chat, another toward numbers and logic. Real example, like a hospital, you don't have one super doctor who does everything. You have a heart specialist, a skin specialist, a bone specialist, each deeply good at their own corner. Part 3. The router who answers. That decision is made by a tiny, fast network sitting in front of all the experts. It looks at the incoming word, sizes it up, and points to the handful of experts best suited to it. This little traffic director is called the router. And here's the key choice. The router doesn't wake everyone. For each word, it picks just a few experts, often only 2, and ignores the rest. Picking only a handful out of many has a name. We call it sparse, meaning most of the model stays switched off for any given word. So the same model can route a coding token toward its code-leaning experts, and the very next token, a comma, a name, a number, somewhere completely different. Every token gets its own little panel of specialists, chosen on the fly. So what's a router? It's a small network whose only job is to look at each word and score the experts. High score, you're a good fit. Low score, sit this one out. Real example, like the receptionist at that hospital. They don't treat you themselves. They take one look at why you're there and send you to exactly the right 2 specialists fast. One word about the word. Inside the model, text is chopped into little chunks, sometimes a whole word, sometimes a piece of one, and each chunk is called a token. The router actually makes its choice per token, not per sentence. Real example, like a deli ticket machine handing out one numbered slip per customer, the system deals with you one slip at a time, not the whole line at once. Part 4. Why most of it stays asleep. Now the payoff starts to show. Say the model has dozens of experts, but the router only wakes 2 per token. That means the vast majority of the network does nothing at all for that token. It just sits there, dark. This gives us 2 different sizes for the same model. There's the total size, everything it has learned, all the experts combined. And there's the active size, only the few experts actually switched on for a given word. Real example, like a giant library with millions of books. The library is huge, but to answer one question, you only pull 2 books off the shelf. You own all the knowledge, you only handle a sliver of it at a time. So you get to have it both ways. The model is big in knowledge, because all those experts exist and were trained. But it's cheap to run because only a thin slice fires for each token. Big brain, small bill. One honest caveat, all those sleeping experts still have to live somewhere. The full model has to be loaded into memory, even though only a few run at once. So mixture of experts saves you computing time, not storage space. It's fast to think, but still heavy to hold. Part 5. Follow one word through. Let's trace a single token, start to finish. Say you're asking for help with a line of code, and the next chunk coming in is the word function. First stop the router. It looks at function in the context of your code, scores all the experts in a flash, and lights up the top 2, let's say a code-leaning expert and a logic-leaning one. Everyone else stays dark. Those 2 experts each take a turn with the token and hand back their contribution. The model blends their 2 answers together, weighted by how confident the router was in each, into one result for this token. Then the next token arrives, maybe an open bracket, and the whole thing happens again, fresh, root, pick a couple, blend. Word by word, the giant model answers you using only a sliver of itself each time. That is mixture of experts. So here's the whole picture. A dense model runs every part for every word, powerful but costly. Mixture of experts splits the model into many small specialists instead. A router reads each token and picks just a few experts to wake. Because only a sliver fires per token, the model stays sparse, huge in what it knows, cheap in what it runs. That's how a frontier AI can be enormous in knowledge, yet quick and affordable to use. But notice something we quietly skipped. We made the AI smart and fast. We never made it polite or honest or careful. Out of the box, a raw model will happily give you a confident, terrible answer. So how does it learn to actually behave? That's the very next video, how ChatGPT learned to behave. If this finally made mixture of experts click, subscribe so you don't miss it. This was Glass Box. See you in the next one.